Okay, so picking up where we left off on this example, if you've read through all of this information, I think that the first easily identifiable region from the rest of this information is probably this last piece right here. They tell us that 137 homes have only a sprinkler system. So again, if we're looking at the region that contains sprinkler systems but excludes ceiling fans and alarms, that would be this region here. And so I'm going to put 137 for the number of homes that would fall within that region. Now from here, we're going to have to work backwards a little bit to find some of our other parts. The next piece of information I used was this piece right here that says that 289 homes have a sprinkler system but do not have a ceiling fan. So if we look in here, 289 homes have a sprinkler system but do not have a ceiling fan. Well, we know that these regions both have ceiling fans. So excluding this area total would have 289 homes. So if we take that 289 homes, 289, and we subtract the homes that we know have only a sprinkler system, 137, what we end up with is 152. That means that 152 homes would have to fall in this region because both of these regions together would have to have a total of 289 in them. So we'll cross that out. Then the next piece of information they tell us is that 439 homes have a sprinkler system. So if 439 homes have a sprinkler system, we've already accounted for some of those with the sprinkler system and alarm but no ceiling fan, and those with just a sprinkler system. So again, I'm going to kind of work backwards. I know that there are 439 homes that have a sprinkler system. I've already counted for 152 and 137. That leaves me with 150 homes in this remaining area. So I don't know exactly how many are in each one of these pieces, but I know that there's 150 homes that would fall between those two regions. So I'm going to go ahead and cross off this because we've accounted for the 439 homes that have a sprinkler system. Now, that's nearly every piece with the exception of these homes that just have an alarm. But I also know that there are 1,000 homes total. And so I've accounted for every region, including the region of those that don't fall within any of our groups. So I'm going to work backwards from 1,000. I know that there are 1,000 homes. I have 101 here with just ceiling fans. I have 72 here with ceiling fans and alarms, but no sprinkler system. I have 152 sprinkler systems and alarms, but no ceiling fans. I have 137 that have a sprinkler system only. And I don't know what these two regions are individually, but again, I know that between the two, they have 150. So if I subtract all of those, making sure, did I subtract the 177? And I subtract the 177 homes that have none of the features from that 1,000, I should be left with those individuals that fall within just the alarm group. And so what I end up with is that there must be 211 homes that have an alarm. So we can cross out that 460. Oh no, I haven't crossed out that 463. We're still using that. Then that last piece of information is that 463 homes have an alarm. Well, again, if I know that this whole region has to total to 463. If I subtract the 211 homes that have just an alarm, the 72 that have an alarm and ceiling fans but not a sprinkler, and the 152 that have an alarm and sprinkler but no ceiling fans, then I should be left with just this piece, which would be 28 homes. So 28 of our homes have all three of the features. And since I know that there's 150 between both groups, if I take that 150 and subtract the 28 that have all three of the features, then I find that there must be 122 homes that fall within this area of just ceiling fans and sprinklers. So this is what our final Venn diagram would look like. So I want to look at some more representations using Venn diagrams that will kind of emphasize what we're talking about when we talk about things being mutually exclusive or when we talk about the complement of an event and so on. So this first Venn diagram that I've given you shows A and A complement. And we looked at this, I believe, 2 lessons ago, but we said that the complement of an event, A complement, contains all the outcomes that are not in A. So if we're looking at this as being our sample space, you're either in A or you're not in A. So the shaded region represents those that are not part of A, and our circle here would represent the events that are in A. So together, those things would make up the total sample space. We've also talked about the idea of events being mutually exclusive or disjoint. We said that they're mutually exclusive if they don't have any outcomes in common. Well, in a Venn diagram, if we're looking at things that don't have outcomes in common, that means that everything is either in group A or it's in group B, but you have no overlapping region because you don't have any events that would happen in both. So it could be in A, or it could be in B, or it could not be in either. But if 2 things are disjoint, then they have no outcomes in common. And on a Venn diagram, again, that just means they have no overlapping regions. So 2 other ideas. If we do have events that are not mutually exclusive, they do have an overlapping region, then we can call that overlapping region the intersection of an event A and an event B. So if A and B do have outcomes in common, then those events that would fall in both, we call the intersection of A and B. So that region would represent the intersection of events A and events B. And we use this symbol here, it kind of looks like an upside down U, to represent the idea of intersection. You can think of intersection as being an AND event. So this is saying things that are in A and in B. So to be in the intersection, it would have to be in both of the events. The union of 2 events, A and B, consists of all of the outcomes that are in either of the 2 events. So if it's in event A or it's in event B, then we consider it part of the union. So notice that if we're looking at the union of 2 events, we're talking about everything that's in group A. So if it's in group A, it's in here, but it's also in that intersection. Or we're talking about everything that's in group B. So if it's in either one of the groups, then we say that it is in the union of those. So we use a similar notation for union. We would read this as A union B. It kind of looks like our intersection symbol, but we've flipped it upside down, so it's almost like a U. You can kind of think of a union as an OR statement. This is like saying those things that are in either A or in B. So it's those things that are in A only, those things that are B only, or those things that are in both A and B. So the way I keep these straight is I kind of think of like 2 different scenarios. When I think of the word intersection, I think of like a street intersection. And a street intersection is the overlapping region between 2 streets. So where those 2 streets cross or overlap is the intersection. And we use the word intersection very similarly whenever we're talking about intersection in probability. It's the things where the groups are overlapping each other. In a union, I kind of think of union as almost like a marriage, like the union of 2 people. So in a union, you're taking things and you're putting them together. So I always use the analogy of when I married my husband. Whenever I married my husband, we had I had just graduated from college and I had this little box TV. My husband, however, had a very nice flat screen TV. And so when we married, we formed a union. And so everything that I got had got combined with everything that he had. So even though I left college broke and I didn't have anything but my box TV, once we formed a union, it didn't matter that I didn't have those things separately in my group because he had it in his group. When we formed a union, all of those things were combined into one group. So now I have a really nice TV. So that's kind of how I think of a union, is almost like a marriage, a combination of two things. So in this next example, they've asked us to draw a Venn diagram for the events, drawing a club and drawing an ace from a standard deck of cards, of 52 cards. So I'm going to first define my sample space. My sample space, in this case, is my deck of 52 cards. So there's two outcomes that we're looking at. One outcome is the event that we would draw a club. So if we're looking at a deck of cards, we have 4 suits. Each suit then has 13. So this set we'll call our event that we draw a club. So there are 13 different cards that we could draw that would be clubs. If we look at the event drawing an ace, I'm going to make it a little bit smaller because there's fewer aces. I'll put ace here. There are fewer aces. So there are only 4 aces in a deck. So there's 4 possible aces. This overlapping region then would represent those outcomes that fall in both. So this overlapping region would have 1 card. It would be the ace of clubs. That would be our intersection, the overlap, which means that there would be 12 cards here in our area of just clubs. Our 13th one would be in the intersection. And there would be 3 cards here in our region that is just aces. And then, again, just the 1 card in that overlapping area. We would also have, in this outside region, the cards that are not aces or clubs. So again, if we take our 52 cards, if we subtract the 12 cards that are just clubs, the 3 cards that are just aces, and the 1 card that is both an ace and a club, then that means that we have 36 cards that would fall outside of that region. So previously we discussed the idea of the addition rule for disjoint events. We said that if 2 events are disjoint, if they have no outcomes in common, then the probability of A or B, we could also write this as the probability of A union B, is equal to the probability of A plus the probability of B. So we're taking the events that are in probability A and in probability and in B, and we're adding the probabilities because they have no outcomes in common. We can also extend this rule to multiple disjoint events. So if we have more than 2 events and all of those events are mutually exclusive for each other, then we can continue just adding the individual probabilities. So if we're looking for the probability of A or B or C, the probability of A union B union C, we could also write it that way. That would just be the probability of A plus the probability of B plus the probability of C. And the idea is that you're either in one group or the other. You're not in both. So the likeliness of any combination of these individual groups is just the sum of each of their individual probabilities. However, if events are not disjoint, if they do have outcomes in common, then we have to take that into consideration and remember that we're counting the same number of outcomes more than once. So for example, if you're interested in finding the probability of a card drawn from a standard deck being an ace or a club, if you take the probability of being clubs and you add the probability of being aces, you've actually taken this overlapping region, the intersection, and you've added it twice. So we must take this repetition into consideration when we're calculating the probability because we've added this region twice. we adjust our formula just a little bit. And this is where our general addition rule for unions comes from. So in general, the probability of A or B, the probability of A union B, is equal to the probability of A plus the probability of B. And when we've done that, we've added that intersection twice. So to account for that, we alter our formula and we subtract it out once. And again, we could think of this as A intersect B. So we adjust this so that we have only added it once into our formula instead of adding it twice. In the next example, it says, based on the Census Bureau's definitions, select an American household at random and let A represent the event that the selected household is prosperous, meaning it has an income greater than $75,000. And let B represent the event that the household is educated, meaning that the householder has completed college. The Census Bureau says the probability of event A being prosperous is 0.125. The probability of event B having a householder who has completed college would be 0.237. And the probability of A and B, meaning that the householder completed college and makes over $75,000 a year, is 0.077. What is the probability that a household selected is neither prosperous nor educated? So if we wanted to draw a Venn diagram for this, we'd be looking actually at, let's just draw it real quick. We'll say A and B here. We're actually looking for the probability of not falling in that area. So really we're looking for the complement of the union of A or B. So if we can figure out the union of A or B, the probability of falling in A or B, then to find its complement, all we would have to do is simply subtract that from 1. So the probability of A union B, falling in A or B. Since we do have an overlapping region, they've told us that the intersection is 0.077. That's going to be equal to the probability of event A plus the probability of event B minus the probability of A intersect B to account for the fact that we've added that value in twice. And then they've told us that the probability of event A is 0.125. The probability of event B is 0.237. And then we're going to subtract the intersection because we've actually added that region twice. So we're going to subtract 0.077. So the probability of either being A or B ends up being 0.285. So then to find the probability of not being in those, we'll say the probability of not A union B, or you could call that the probability of A or B complement, if you want, would be 1 minus the probability of A or B, which would be 1 minus 0.285. So 0.715 is the probability that an individual household would fall outside of the union of those two events, those that are neither prosperous nor educated.